Hey guys, and welcome to the first video of the semester with these sort of lecture style video series. So normally what I'll be doing for each video is going over the blank chapter notes that I have up on Moodle for you guys. And what I'll do is I'll go through several pages of this material and I'll be going over what is on each page, going in more depth with some of the points I've written out, going over some examples, and hopefully what that can do for us is when we meet in lecture, whether it's in person or over Zoom, is we can go into a little bit more depth with things. We can do some more problems. We can go over some questions you guys might have about what was covered on the videos, and just any sort of clarifying points or whatever you guys want to talk about during the lecture. So what I'll do typically for the first portion of the chapter is give you guys some practice problems to do. So with these practice problems, you can do them on your own, and they don't count for any points or anything. But what we can do with them too is we can maybe go over them during lecture. They might show up on a quiz or homework, but for the most part, these are just practice problems for you guys to do on your own. So with organic chemistry, right, so it is the study of the chemistry of carbon-containing compounds. And like I kind of talked about in class a little bit, for the most part, when we look at the periodic table, we're really kind of just looking at the first row, primarily hydrogen, and the second row of the periodic table. So that's where we're going to be finding most of the majority of the elements we'll be talking about during class. So with this first chapter, structure and bonding, hopefully a lot of this will just be a review for you guys. There might be some new material later on, but I hope for the most part, again, this will just be a review for a lot of you. And if anything does seem, you think you've seen talk before but don't quite remember it, or go through a video and I didn't quite understand that as well as I thought I should have, maybe just go back and look at your general chemistry notes and just get kind of refamiliarize yourself with some of these concepts, even just looking at old exams just to remember what your thought process was on everything. Right. So just jumping right into it. So the first thing we'll talk about is bonding. And the first section of that will be talking about Lewis structures, right? So Lewis structures are the depiction of valence electrons for an atom, that is the electrons in the outermost shell, right? And if you remember from the periodic trends, right, that you learned about in General Chemistry 1, depending on what column an element is in, that kind of tells you how many valence electrons they have. So, right, so hydrogen has 1, boron has 3, carbon has 4, and sort of so on. And when we're thinking about that, right, how do we know that that element has that many valence electrons, right? We can look at the column and say, like, yeah, it has, carbon has 4 valence electrons, but how do we know that, right? So let's take a look at this example here, methane, and let's talk about how we know that carbon has 4 valence electrons and how we know we can make 4 bonds. So to do that, we have to remember electron configuration. And this is definitely something you might want to just go back and briefly review. I'll talk about it a little bit here, but I won't be mentioning it too much during the course of this chapter. But just for the sake of remembering, let's go over it a little bit, right? So with carbon, right, carbon has 6 electrons, but only has 4 valence electrons. So when we do that, we have to go through the electrons and where they lie in the orbitals for carbon, right? So carbon has a 1s orbital, right, and that is completely filled, right, with 2 electrons, and that is in the inner shell. So we go right to the second row with the 2s and 2p orbitals, and drawing those out, it's 2s orbital that has 2 electrons in it, so that is filled. And then we go on to 2px and 2py, and those are also filled, right? And according to Hund's rule, right? It states that when there are two or more orbitals of the same energy, electrons go into different orbitals, right? So that's why you don't see 2px2, because the p orbitals are in higher energy than the s orbital. So, right, the 1s orbital is in the inner shell, and these four other electrons, which are occupying the 2s and the 2p orbitals, those are in the outer shell. And that is why they are the valence electrons, because they are in the outer shell. Make sense? So now let's look at carbon, or this. So let's look at methane and its Lewis structure. Right, so carbon, right, as we discussed, has 4 valence electrons that it can do bonding with when it shares electrons with something else. And there are 4 hydrogens on this molecule, and we know that hydrogen has 1 valence electron. So it shares an electron with carbon, so that hydrogen can achieve noble gas configuration, right? Helium, and that way carbon can fill its octet rule, right? So it has 8 electrons around it, so that it can fulfill its own electron configuration to achieve noble gas configuration. So another way we can sort of draw this out, right, is that instead of drawing 2 dots for 2 electrons, we will just draw a line instead, which tells us that there are 2 electrons between carbon and hydrogen, right? So what I have here for you guys is just a, as stated, common bonding patterns for uncharged electrons. So with carbon, right, as we just discussed, it has 4 valence electrons, so it can make 4 bonds. Nitrogen has 5 valence electrons, right, but remember it only has 1 s and 3 p orbitals to use. So once all those are filled, the next electron has to pair with another electron, right? So that's why we get that unshared pair of electrons, that lone pair. So nitrogen now can only make 3 bonds, right? And same with oxygen. It has 6 valence electrons, so that means there must be 2 lone pairs, so it only makes 2 bonds. Hydrogen, of course, we just said, is 1, and the halogens, including fluorine here, has 7 valence electrons. So there are 3 lone pairs and 1 quote-unquote free electron to make a bond with. There's other elements too we can look at in that same row. So beryllium just has 2 valence electrons, boron has 3, and of course noble gases like neon have 8 valence electrons, and so traditionally we do not see them making any bonds because they have a filled octet and they are satisfied. So now let's talk about some more specific kinds of bonding. I've mostly been talking about covalent bonding so far, but let's talk a little bit about ionic bonding. So ionic bonding is the loss or gain of electrons to form a bond to satisfy the octet rule and obtain noble gas configuration. Kind of like we just sort of discussed, a filled shell of electrons is stable, and atoms will transfer and share electrons in a way to attain this stability. So ionic bonding in general is pretty common in inorganic compounds, right? So without carbon, and typically uncommon in compounds where it's organic, so mostly carbon-containing compounds. So let's take a look at potassium bromide here. Right, so in their quote-unquote neutral form, potassium just has that 1 valence electron, and bromine has 7. So the way the ionic bonding will work is the potassium atom will share its electron to bromine in order to attain that electron configuration of a noble gas. So potassium will transfer, not share, I misspoke. Potassium will transfer the electron to bromine, right? So potassium is now charged and has argon configuration, and bromine now has 8 electrons, so its octet rule satisfied, and it has a krypton configuration, right? So both of these have their octet rule satisfied, they both have that noble gas configuration, so they are happy. Typically the way that we portray an ionic bond is not like this with a plus sign, but rather, just like this, with the atoms next to each other and their charges on display. I'll talk a little bit more about formal charge in a couple slides here, but hopefully that is something that you are familiar with. And yes, this is an ionic bond. All right, so next let's talk about covalent bonding, which we've kind of been talking about a little bit already. So in this case, instead of transferring electrons, they are sharing electrons to satisfy the octet rule. And this is the most common form of bonding, and for the most part, 90% of the time that's what we'll be seeing and discussing when we talk about bonds between atoms. So the second row elements are typically the most stable with 8 valence electrons. And that typically comes from them having the 2s and 3 2p orbitals, right? So each orbital can only have 2 electrons. So with 1s and 3p orbitals, that's 8 electrons. Third row and beyond can have expanded octets due to those lower lying d orbitals. We won't be talking about that too much in this class, but just something for you to know in case it does come up somewhere, especially in your reading. Covalent bonds typically are strong between the bonding atoms, but intermolecular forces right between them lead to lower melting point and boiling points compared to ionic bonds. And we'll be talking about that a little bit more next chapter, but just something to keep in mind. So let's take a look at chlorine, or I guess technically chlorine gas, if we are considering it to be at standard temperature and pressure. So chlorine, right, as we discussed, has seven valence electrons, like so. And what we'll see is that the chlorine we want to share those valence electrons with each other so that they can each have their filled octet. Right? If chlorine was just to transfer one electron over, this chlorine would be satisfied, but this one would now be missing an electron and would not have a completed octet. So what's going to happen is the chlorines will share that electron between each other. And we see that chlorine now, or Cl2, chlorine gas, it is now satisfied. Each chlorine has access to 8 electrons, right? So this chlorine has access to that shared pair of electrons between it, and this chlorine over here also has access to that shared bonds between it. And of course, as discussed before, each chlorine atom shares an electron to get noble gas configuration. Therefore, completing their octet rule. Right? So hopefully that makes sense. And again, covalent bonding is what we'll mostly be talking about in this class, and it'll be something that comes up again and again. And ionic bonding will kind of just be there in the background, especially when we're talking about some of these later chapters. So, kind of an example of that, I guess. Sometimes when you have a mostly covalently bound compound, it may also have a charge with it. So you'll see kind of a combination of both covalent bonds and ionic bonds. So let's take a look at this example here. We'll talk a little bit more about how I kind of look at this molecular formula and come to drawing out a Lewis structure like this. Oops, too many electrons on that one. So we have this molecule here, and we have this oxygen here that is negatively charged. And again, we'll talk about formal charges in about a minute here. So we also have the sodium atom, right? So sodium, I'll show up here, and as drawn, right, kind of like we just discussed, sodium will not have an electron on it, as it has sort of transferred that already to the oxygen. So it is positively charged here, right? And so what we wouldn't want to do, for example, is we wouldn't want to show a bond like this to that oxygen, right? And that's mostly because while the oxygen, right, has its octet rule satisfied and has noble gas configuration, the sodium atom is not happy. It has 2 electrons technically that it owns, so it does not have its octet rule satisfied. It does not have that noble gas configuration. It would much rather appear like this and have this ionic bond as opposed to a covalent bond, right? So we do not want this, right? So hopefully that makes sense. And this is just kind of an example of something we'll see a lot next chapter when we start talking about acids and bases. We'll start seeing this combination of both covalent bonds with typically 1 ionic bond to that molecule. So this is just an example to show you that both types of bonding, covalent and ionic, can exist in the same compound. All right, so formal charges. We're talking about that a little bit already, but let's talk a little bit more about what it means and how we can recognize when when an atom is charged, right? So an atom's formal charge is defined as the number of valence electrons in the neutral atom before bonding, so it's group number. And that is minus the number of unshared electrons or lone pairs on the atom in the structure of interest. Also minus half the number of shared electrons bonds on that atom. So this is one of the few cases where we'll be doing some math in this class. So when we're looking at formal charge, right, essentially, so like there is this equation down here, it was kind of explained up here. This equation will help you guide through looking at formal charge, but essentially all you're doing is you're looking at the number of valence electrons an atom currently owns, and you subtract that by its neutral atom state. So with carbon, right, it has 4 valence electrons, it's neutral with 4. If it had anything less or more than that around it, it would have a charge. So let's look at an example of this. So let's look at NH4, nitrogen with 4 hydrogens on it, right? So how do we know if nitrogen here has a formal charge or not? So let's first look at the actual formula I've written up here. So how many valence electrons are on the atom, on the neutral atom rather? Right, so nitrogen, remember we're looking back at the periodic table, it has 5 valence electrons, right, when it's neutral. So now how many unshared electrons are on nitrogen? 0, right? Right now it has 0. And that's subtracted by half the number of shared electrons that the nitrogen currently has. Right, so nitrogen here, right, so there are 8 shared electrons around it. So half of that is 4. So it has a formal charge of +1. So the nitrogen atom is positively charged. Another way to look at this, kind of without so much of the, it's not really that much math, but without really thinking about the math too much, what I tend to do when I'm looking at this is I think, okay, nitrogen is neutral, quote unquote, with 5 electrons, and it currently owns 4, right? Because there are 8 electrons around it, right, from sharing electrons between the hydrogens. But in each of those bonds, we can say, okay, there's really 1 electron that the nitrogen owns between those bonds. And so thinking about it that way, you just simply, right, so if it's neutral with 5, and it owns 4, and that is +1, right? Positively charged. For another quick example, where there's one where there's a lone pair on it, let's take a look at a different hydrogen bonded nitrogen. So here, right, you can see that there are 3 hydrogen atoms, so there's 3 covalent bonds to it. So nitrogen does seem like, its octet is satisfied, right? There's 8 electrons around it, with this lone pair up here as 2 more electrons. So there are, right, so with nitrogen, it's neutral with 5 electrons, and around it, there are 5 electrons, right? So with each of these bonds, if it owns 1 of those electrons, and then it owns these 2 electrons up here, it owns 5 electrons, right? So it is neutral. Looking at the formal charge equation for that, going into the actual math behind it, right? So 5 valence electrons in neutral nitrogen, number of unshared electrons, so 2, right, because 1 lone pair, and then half the number of shared electrons, so there are 6 shared electrons, right, from each of these covalent bonds. So that is 3. So 0. So it is a neutral molecule, neutral compound. And so in general, and this will kind of play a larger role in a little bit, when there are fewer formal charges on a molecule, the more stable it is. And if when we start having to draw structures from molecular formulas, when you're connecting atoms together, you want to, A, make sure the octet rule is satisfied, but you also want to make sure that we have the least charged structure possible, right? Because the less charges that are on a molecule, the more stable it is. Right, so hopefully that makes sense. And again, I would encourage you to take a look back at your Gen Chem 1 notes, just to make sure you do kind of understand formal charges, and whether you want to just use a formal charge formula or kind of do the more casual approach like I did. You're just looking at the neutral atom subtracted by how many electrons that it quote unquote owns. That's fine too, whatever way works. So the last thing we're going to talk about here is bond polarity. Or dipole moment is probably something you've heard a lot in your first semester of general chemistry. Electrons, of course, are not always shared equally in a covalent bond. Typically, the bond is more polarized, with electrons more strongly pulled in one direction depending on how electronegative an atom is. And bond polarity is measured by its dipole moment. That is the amount of partial charge carried across that bond. And another example of remembering periodic trends, we have to think about electronegativity, right? And in general, right, the more to the right we are on the periodic table, the more electronegative an atom is compared to other atoms to the left. So electronegativity is used as a guide to predict the direction of dipole moments across bonds. And atoms with higher electronegativities, of course, are going to pull those electrons more towards themselves. And we've seen using we've used positive and negative charges, but we can also use partial charges. Right here is kind of signified by delta to denote when an atom carries less or more charge due to this bond polarity. So let's look at an example. So right here, H2, just hydrogen gas, at standard temperature and pressure, of course. We can look like this, and of course there is no difference in the electronegativity of one hydrogen atom to another, right? So there's no difference here. So there is no dipole moment. So this is what we would call a nonpolar covalent bond. And so if we want to think about where the electrons are in this bond generally, we can sort of look at it like this. Right, the electrons are kind of just in the middle. They're not really pulled to one side or the other, so there is no dipole moment here. It is a nonpolar covalent bond. So now let's look over here to this molecule. Let's drawing out the Lewis structure for this. Right, so what do we see here? Remembering our electronegativity periodic trends, again looking towards the right, those elements are more electronegative. Chlorine is more electronegative than carbon. So the electrons are going to be pulled more towards chlorine than towards carbon. And there's a little bit of difference here between hydrogen and carbon, but for the most part we won't really concern ourselves too much with that, but carbon is a little more electronegative than hydrogen. But in this case, with chlorine being much more electronegative than carbon, that's kind of where we'll be focusing. So the way we kind of denote that, right, that difference in electronegativity is with this dipole moment bond, like so. And we can say that chlorine has a partial positive or partial negative charge on it, and carbon has a partial positive charge on it. And the way we can draw that as well to sort of show where those electrons are lying. And kind of put them right here. And say that in general the electrons are lying more towards the chlorine than they are towards the carbon. And so this is what we would consider a polar covalent bond. And we'll be getting more into dipole moments and this bond polarity in later chapters, but it is one of the important concepts from your first semester of general chemistry that is important to review before moving onward.